All right, so we're going to take a look at 8.5 pretty much all week. We'll just split it into 4 parts. We're going to be looking at what are called vectors. So we're going to do a couple things. We're going to look at how we can basically look at vectors visually by actually drawing them. And then we're going to get away from drawing and look more at vectors as just numbers. Right? Both have their kind of advantages depending on what you're trying to do. But I think visually, at least at first, makes it easier to understand. A little bit slower than just using numbers, but it makes it very like something you can see in front of you. And basically, what a vector is used for, a lot of times you see them used in physics. And they are used to represent something that has a magnitude and a direction to it. So an example of something that would have a magnitude and a direction would be velocity. Now, velocity is different than speed. The difference with velocity is velocity not only tells you how fast something is moving, but the velocity also tells you the direction it's moving. So if I were to try to describe, say, the motion of an airplane, a perfect way to do that would be use a velocity vector, because it would describe the speed of the airplane and it would describe the direction. So if I bring up this website, okay, this shows a whole bunch of different planes, okay, that are in the air right now. And if I click on one of them, I can see the speed and the direction. So I just click on one. So, there it is. All right, so let's see if I can find the speed. If I scroll down, there we go. So the speed is 552 miles per hour. And the direction, well, what they call it in a plane is they call it a route. So I can see all these different letters. I don't really know what those mean. But if I look at the path of the airplane, it's basically traveling southwest. All right, because Paris, I'm trying to think if the map is a little distorted, but it's going from France to Miami. So that's definitely west and south. So west on a compass, that's a heading of, let's see, they put north at 0, 91. So west is 270. So if we look at the route, we're probably going to see some directions of 270 and probably 180, around between 270 and 180. Now it does go north a little bit at first, but not much. So let's click on the route and see if we see angles around 180, 270. Yeah, lots of them. So between 180 and 270. So all these angles indicate the direction. And this is a little more complicated because the plane goes in many different directions. It's not just going in an exact straight line. Right. But definitely a lot of 180s and 270s. Right. So that's one example where you could use a vector to describe the speed and the direction. Another example is force. So force describes two things: how hard you're pushing or pulling on an object, and what direction are you pushing or pulling. You know, are you pushing down? Are you pushing sideways? That's different directions. Right? So force is something else that we could write a vector for, and it would describe exactly the direction and how hard you're pushing or pulling on it. If you want to represent a vector visually, you can think of it as an arrow. So imagine all these airplanes, right, in like a computer system. These are all different vectors. And it's the job of each airport to control the traffic coming into and leaving in their area. So they try to make sure everything is spaced out so it's safe, things like that. So really, you might be looking at hundreds, maybe even thousands of vectors at the same time, A little more complicated because it's 3D. So two planes that look really close. One of them could be on the ground, and one of them could be 30,000 feet in the air. So you have to take that into account too. But all these vectors have to be coordinated, and that's what the airports do, coordinate the traffic. There we go. So if you want to represent a vector visually, a vector has to represent two things, a magnitude and a direction. The magnitude can be represented by the length of the arrow you draw. So if these are two airplanes, they're both traveling east, but the bottom one is traveling twice as fast as the top one, because its vector is longer. So the length indicates the magnitude, and the way it points, because it's an arrow, naturally indicates direction. Right? If these were forces, let's say I had an object like a box, I was pushing like that, and another force was pushing like that. Well, the forces are different, one because one's pushing right, the other one's pushing up. And the one pushing up is a lot stronger than the one pushing to the right because it's longer. Any questions on that? So when we describe things about vectors, we can borrow a few things that we use in geometry. Generally, a vector is an arrow. So it means it starts somewhere and it stops somewhere. The arrow doesn't go on forever. If it did, that would represent like a plane that goes infinitely fast. That doesn't happen. Where the vector starts is the initial point, and where it stops is the terminal point. If we wanted to describe this shape in geometry, what do you call something that looks like an arrow in geometry? There's a name for that. Remember, yeah?
Is it array?
Array. Yep, array. Continues in one direction. Our ray stops. Technically, a real ray goes on forever, but these stop. Now, in geometry, the notation you use for that is something like this. What that means is start at P and head towards Q and draw an arrow from P to Q. Well, we're going to use a little bit different notation, but we're going to borrow some of it. We can represent a vector just using a single letter. But what do we already use single letters for in math? All over the place. Yeah?
Variables.
Variables. A variable and a vector are totally different things. It's like a triangle and a square. They're totally different. So single letters are already used for variables. So what can we do to use a single letter but tell the person reading it it's a vector and not a variable? There's two things you can do. One thing you can do is take your letter and put an arrow on top of it. This indicates that we're talking about vector M. So if I use this one up above, I could say this is a picture of vector M. The M doesn't tell you at all where it starts and where it stops. So you'd have to say, okay, vector M, you'd have to scroll up to where you find the diagram for vector M, and then you could look at where it starts and stops. The geometry notation tells you that automatically. So it's kind of a downside, but that's one way you can do it. You can use a letter with an arrow on top, or you can just make the letter bold. And if you look, like in the homework tonight, that's pretty much how they do it. They use a bold letter. I don't know how easily you can tell, but that V and the W and the U, those are bold. They're supposed to look bold. And there's some other bold letters out there too. So anytime you see a bold letter, that's a vector. Vectors can be capital or lowercase, either way. The book uses capital sometimes it uses lowercase. Okay, so any question on that? So we're going to start by looking at some real basic things we can do, which is just taking two vectors and adding them together. But we're going to do it visually. So imagine that that dot represents an object, like a box. And there's a force pushing right, and there's another force pushing up at the same time. How is that object going to move if both those forces push on it at the same time? Another way to think about it is pretend like it's a sailboat on the water. And there's wind blowing up and there's another wind blowing to the right. How would the sailboat move? Yeah?
Is it diagonal?
Diagonal, yeah. It would move up and to the right. And if you want to see exactly how it would move, let me just break this apart into two vectors so I can show you. Ungroup it. This is the one that points right. This is the one that points up. That's the one that represents the actual direction and magnitude for the boat. It's like making the diagonal in a right triangle. So this is the result of these two vectors pushing on the boat at the same time. It's going to go up and to the right. And notice it's longer than the original two. It has to be, because it's a hypotenuse. Hypotenuse is always the longest side. So when you combine two vectors together by adding them, the result is a new vector. The vector can have a new direction and a new length. Now, the direction doesn't have to be new. Imagine two people, like, let's say a car broke down and two people were pushing a car from behind it. Well, you're both pushing in the same direction. So that's an example where maybe you're pushing that hard, somebody else is pushing just as hard, so the result is an even stronger force pushing, but it's in the same direction. The direction doesn't change because you're working together. So let's look at another example of just taking two vectors and adding them graphically. Let's say that's vector v, and this is vector w. I'm going to show you one more time how to add them visually, and then I'll write it all up. You basically position them so that the end of one lines up with the beginning of the next. So here's v. Here's the end of v. Here's the beginning of w. Line those 2 points up. Just like this. That's step one. Position the terminal point of v and the initial point of w so they're the same spot. Then connect the start to the finish. The finish is always where the arrowhead is. Okay, follow the direction of the arrows, that's where you finish. This is where you start. That is the answer for v plus w. And again, I'm just trying to get you used to, I could write it in bold, or I could have put the little arrows on top. I could have done it either way. But that's the picture. And that's some of the questions in the homework and on the test. That's what you have to do. You have to make a sketch, just like that. All So what did I do? I positioned the two vectors so that the ending point of V was right on top of the starting point of W. That's the first thing. So line them up so they look just like that. The last step is to draw from the initial point of the first vector, which we call V, to the terminal point of the second vector, which we call W. And that's how you add two vectors. Now, I only did it for 2, but you can do it for 2 or you can do it for 20. It doesn't matter how many you want to add together. Let me show you an example where I add 4. Again, just a vision. That's all I'm going to do.
I have a question. How do you know what ways like the arrows go?
Well,
How do you know?
they'll give you a problem like that.
Oh, so they give you the arrow.
They'll give you the 2.
And then you would make the connecting one.
And then you have to add them and make a connection.
Oh, okay.
Yeah. So that's a problem we're going to do. So let's say they gave you 4. 1, 2, 3, 4. And you wanted to add all 4 of those together and see what's the result. Take that one, plus that one, plus that one, plus that one. The flow of the arrows should always go in one direction. If you did something like this, that's wrong. Now it's like you have 2 arrowheads hitting each other. That's like a collision. It should always flow. Think of it like a pipe. Right? The water comes in here, it flows, and where it comes out, that's the end. So the final answer is connect the start to the end, and that's it. So that's the result of adding all 4 of these together. Now, do you think it matters the order that I add them on? Let's just make them different colors so we can keep track. Make that the green one, and make that one blue. What do you think? Think the order matters? Does it matter with numbers? When we add numbers together? No. So let's try it in a different order. This is black, red, green, and blue. All right, well, let's start with green then. And then let's put black on the end. Then let's put blue on that. And then let's put red on that. So we should be able to connect. This is, I don't like adding it this way. It looks more confusing to me. But you're going to connect the start point of blue, or no, that's black. The start point of black to the end point of blue. So the start point of black is right here. The end point of blue is right here. And that should be the same arrow. Yeah, it looks like I didn't do it perfect, but that's the general idea. So it doesn't matter the order you add them in. Right? Again, I think, I don't know, that way it looked kind of confusing to me. But let's do it like that. That looks a little clearer. So now, connect the start of green to the end of blue, because this is the start. That's the finish. And this arrow should slide right in there perfect. Yeah, pretty close. All right. I try to add them in an order that it looks clear. I think that was the clearest way to do it. Once they start crossing over each other, then it looks confusing. All right, any question on that idea? So when you're adding them, you have to think ahead a little bit. Okay? Where do you want to start on your graph paper? both of these vectors have a component that points to the right. So I would not start on this edge of the paper. Start pretty far to the left, otherwise you're going to go off the paper. And that can be harder to think about if you have like 5 or 6 vectors you have to add. Where do you start? You can either get a giant piece of paper and start in the middle, or try to think about it ahead of time. So here's V, just like that, and W, just like that. So how would I visualize V plus W? What do I have to do now? Yeah?
You would do it across at the top.
All right, how can you be specific about which way I would go?
You'd go to the right, like from the left top down to the right arrow point.
Yeah. So that right there is V plus W.
Does it matter what, like, how you, like, what shape you make? Like, let's say you did, like the bottom.
Like if you did the bottom one first?
Yeah. Like
So if you did the bottom one and then put that one on the end of it,
yeah, would that matter?
technically that's now W plus V,
Um,
but it's exactly the same thing. So the order that you add them up in does not matter, but follow the order that they say. So V plus W means do V and then do W. Okay, question on that? All right. What do you think is going to happen here? When I add V plus W this time? Ashley?
it's gonna overlap.
Okay, what do you think the result is going to be? Yeah.
Straight line.
Okay, so straight line. Anyone else have another thought? What would happen? Pretend like these were two forces pushing or pulling on an object. Like, what would happen to the object in this case? Chris?
It would stay where it is.
Yeah, it would stay right where it is. Basically, what's happening here is everything is balanced. Because you have a force pulling, or a force going right, and a force going left, and they're exactly the same length. So the way you're supposed to do this is take the end point of one and line it up with the start point of the other. So you're supposed to line the red dots up. Once you line those up, then you're supposed to connect green dot number 1, which is where you start, to green dot number 2, which is where you finish. Well, let's line the red dots up and then see what happens to the green dots. So I'm doing the same thing I did in the last problem. The green dots just became the same point. So there is nothing to connect here. You have no diagonal. So what happens in this case is the answer is this. That's called zero vector. You can either write it like that, or you could write it like that. Whenever you add two vectors together, the answer is a vector. You never get a number when you add vectors. So you can't put the number 0 here. You have to put a vector. Well, the vectors are canceling each other out. So we call that the 0 vector. The magnitude of the 0 vector is 0. It has no length. And since it has no length, you can't really tell which way it's pointing. So this is the only vector that doesn't have a direction. It's kind of a special piece. Any question on that idea? And so when vectors cancel out, and the start point and the end point are the same, when you line them up, that's the answer, the 0 vector. All right, so a couple properties about vectors. First of all, vector addition is commutative. I've already shown that to you. That means you can change the order you add things up in, and you will get the same answer. I'm not going to show this to you. Okay, I'll show you the next one. I've shown this to you a couple ways already. So the order you add vectors in doesn't matter. Now, associative, that's a different property. If you think about the word associate, when you associate, do you do that by yourself, or do you generally associate with like a group of other people? Yeah. Right. Associate means like if I said who do you associate with? Who are the group of people that you hang out with? Associative means group. And the way we group things in math is with parentheses. So this is the associative property. The order is exactly the same on both sides. I'm not changing the order. I'm changing what I do first. I'm changing the grouping. Here I'm going to add A plus B first. Here I'll do B plus C. And I'm going to show you it doesn't make a difference. So it might be easiest just to watch this. It's up to you. Here's 3 vectors. And let me do A plus B first. Here's A plus B. And that is A plus B. Let's move that, put that back. So this is A plus B. Now, I'm going to add C onto the end of that. So there's C added onto the end. So on the left, the final answer you get is that. That's A plus B, then plus C. Now, let's try doing it. I'm done with that. Let's try doing it the way it says on the right. Add B plus C first. Here's B plus C. Connect your diagonal. Just like that. Okay, I'm done with those. So that's B plus C. Now take A and put that on the end of it. Here's A. Put that on the end of it. There we go. And connect your diagonal. And the hope is it looks the same as the other one. Let's see how it did. Yeah, looks pretty good. They look almost the same. Actually, they almost look exactly the same. That's the associative property. Any question on that idea? So if I'm given a choice to add a bunch of vectors together, I try to do it in a way that it looks nice, like I showed you right here. This looks nice and easy to follow. I think you could make it look more complicated if you did something like this. It's a little harder to follow now because it's kind of overlapping itself. So I try to just pick an order that makes it look nice. That's not wrong. Okay, you can put it like that. You can do that because the arrows are all following one path. But well, it's up to you. All right. What do you think the difference is between having a vector and putting a negative in front of it? What do you think? Think about it visually. What do you think putting a negative in front of a vector would do to it? Drawing. Yep.
So flip it around.
Yep, it would flip it around. So the difference between those two is the direction they point. But they would both have the same one. Different direction, but they have the same, yep, same magnitude. If you want to visualize an example of a vector and its opposite, just think back to example 2. Right here. These vectors are opposites. And that's exactly what we just came up with in example 2. If you add a vector to its opposite, you get the 0 vector. Now, this idea right here, adding a negative, is basically going to lead us into the next thing, which is subtracting 2 vectors. We already know how to add them. We're going to try to use that same thing for subtraction. So here's an example. How could you think of 3 minus 2 as an addition problem? Let's say you had to explain that to somebody that doesn't understand subtraction, but they understand addition. So you say, okay, I can write it a little different. Yep.
3 plus -2?
Yeah, 3 plus the opposite of the second number. That's how you could explain subtraction. It's addition with the opposite. Here's your first number. Here's your second number. The opposite of the second number. We're going to do the same thing when we want to subtract a vector. We're going to find the opposite of the second one, flip it around, and then add it. And that's how we'll do subtraction. So to subtract 2 vectors, take the second one, flip it around, that makes it the opposite, and then add it. Adding the opposite is subtraction. And that's how we'll do it. Let's look at that. So they want us to find v minus w. First, can someone tell me how I can think of v minus w, just like I did 2 minus 3, as an addition problem? Francesca?
V plus negative.
Yep, v plus the opposite of the second vector. And Jack just told us that when we see a vector and it has a negative in front, it just means flip it around. So the easy way I can do that quick is just trace over it and have it point the other way. Okay, so now I have negative w. So now do what it says. Take v, add negative w on the end of it, and make your diagonal. There you go. That is the vector v minus w, because we added the opposite. We subtracted. Any question on that? Multiplication. So we just took 2 vectors and we added them. We took 2 vectors and we subtracted them. This is not multiplying 2 vectors. This is what we call scalar multiplication. We are going to look at multiplying 2 vectors. That'll be on Thursday and Friday. Scalar multiplication looks like this. It's when you take a vector and you multiply it by a number in front. This number is called a scalar. Now, I haven't explained it yet, but does anybody have a guess what the vector 3v would look like compared to just v? What do you think would be different about 3v? Yeah?
3 times as long.
3 times as long. So that's one thing that a scalar can do. It can make a vector longer. Anyone have another guess what else a scalar can do? Yeah?
It could also make the vector shorter.
It could make it shorter. And one more thing. Longer, shorter, And we kind of talked about this in the last thing. Yeah?
Can it change the direction?
It could change the direction if you put what kind of number?
A negative?
A negative. It could flip it around. Yep. That's the three things that a scalar can do. So this is when you multiply a vector by a number. The result is always a vector. The vector will be one of three things that you guys just said. Could be longer, could be shorter, or it could flip direction. I mean, I guess you could say it could stay the same, but then you're just scaling it by 1, so that's not really scaling it. And if you forget, the way I try to remember it is think of like a scale model. If you make a scale model of like a car, you're probably making a smaller version of the same thing. It's just a smaller version. So it got shorter, like a vector. If you were making a scale model of maybe like a molecule in chemistry, well, you're probably going to make a bigger version. You're going to scale it up so you can see it. So it gets longer, it gets bigger. And so it can shorten, lengthen, or reverse the direction. All right, we'll try a couple examples where we take a vector and scale it. All right, so directions say here's v, so this would be given. I want to find 2v and a half v. All right, using the smartboard, how could I get 2v perfect? Like exactly 2v. Yeah?
You could copy over the first line twice.
Yeah, just make 2 copies of v and stack them together. You don't have to measure or anything like that. There you go. That's 2v. Just draw it. So if this was a velocity, what does 2v mean compared to 1v? What would be the difference if this was an object traveling and this was another object? Yeah?
2v goes twice as fast.
Yeah, they're both heading to the right, but 2v is going twice as fast. If they were forces, 2v is twice as strong. And then a half v, I don't have a good way to do that on the smartboard other than estimating. So I would say a half v, maybe about like that. So same direction, half as long. Any questions on scaling a vector? Let's do this one. So this combines both things. It takes addition and scaling and puts it together in one problem. Let's just do the first one. So I'm not going to worry about this one. Let's do 2v plus 3w. So Abigail, how many of the v's do I need? 2. And v goes up and to the right. And Casey, how many of the w's? 3. And that goes down and to the right. So I should probably start closer to the left because I need to go to the right quite a bit. So let's take 2 v's, put those together. Okay, like that. And now put 3 of the w's on the end of it. All right, so there's 1, 2, and 3. That looks pretty good. And now connect the start to the side. Works better if you use a straight edge. I just estimated that one. That wasn't too bad. There you go. 2v plus 3w. Okay, question on it? All right, so working with vectors, sometimes we don't care about the direction. All we care about is the magnitude, and there's a symbol for that. If they specifically want to talk about the magnitude of a vector, what they'll do is take the vector and put double lines around it. This symbol means magnitude. So in other words, they're asking you, how long is the arrow? And because magnitude represents how long something is, it's always a positive number. You can't have something that would have a negative length. So what do you think the difference would be between those two things? The magnitude of v and the magnitude of negative v. What would be the difference between them? Yeah?
They're the same.
They're the same. Some people say to me, well, they point in opposite directions. That's not what I asked. I asked what the difference is between the lengths. And the answer is nothing. They're exactly the same. Okay, so we're not going to focus too much on finding the length today, but I just want you to know the symbol. Let's see, what else? When we talked about trig, we did it on a certain size circle at one point. And that circle had a radius of 1. Does anybody remember what we called that circle? Circle with a radius of 1? It was a blank circle. Yep.
Unit circle.
Unit circle. Well, I'm not going to talk about circles, but we're going to talk about a vector with a length of 1. And that's called a unit vector. Very important concept for what we're going to do almost the rest of the week. A unit vector is a vector that has a length of 1. Any question on that definition? All right, so the drawing vectors is great. I mean, I think it's really helpful when you have a word problem and you're trying to visualize something. But if you don't have to visualize the problem, drawing it just takes more time. So we want to start to talk about ways that we can represent vectors rather than using arrows. And that's where we get into just writing numbers. So I'm going to show you, between today and tomorrow, 2 different ways that you can write a vector without drawing it. But I'm going to show you one way today, and I'll show you the other way tomorrow. The first way of doing it is what is called an algebraic vector. Now, I don't know if that's specific to our book, but I haven't seen that term in other books a lot. But that's what our book calls it, so. And the way an algebraic vector looks is just like that. Now, how can you look at that and know it's not a coordinate? Because it looks similar to a coordinate, but there is a pretty big difference. Anyone see the difference? Yeah.
There's no parentheses.
Yeah, there's no parentheses. It uses these angled brackets. I guess if you were using a key on a keyboard, it might be like the less than and the greater than. I think that's as close as you'd have to it. And A and B represent what we call the components of the vector. So let me explain what I mean by a component. A two-dimensional vector can have two components. A three-dimensional vector can have three. So I'm going to make up a vector and I'll show you the components. The vector 2, 3. Here is the vector 2, 3. 2, 3. I would say this vector has a horizontal component of 2, and it has a vertical component of 3. The 2 and the 3 explain how far right and how far up you go to get from the start to the finish. Here's another example of a vector 2, 3. Here's another one. Here's another one. These are all the vector 2, 3. This notation doesn't tell you where to put it. You put it wherever you want. There's a common place you usually do put it from. But in general, you go 2 to the right and you go 3 up. And that's all you have to do. If they say to sketch it, you can put it wherever you want. So think of this. Think of the 2 and the 3 as directions that tell you from an initial point how far left and right to go. That's A. And then how far up and down to go. That's the B. To get to the terminal point. So it's directions from the initial to the terminal point. So A, because it tells you left and right movement, we call that the horizontal component. And B tells you the up or the down movement, so we call that the vertical component. Now again, what this notation doesn't tell you, this notation right here, it does not tell you where in the plane to put your vector. It doesn't tell you what the position should be. So that's what I'm just explaining to you. So I guess technically you have the choice to put it anywhere you want. But out of all the ones that I just did on the board, where do you think the most common starting point would be? There is one up there that would be used more often than the others. Chris?
The origin?
The origin, yeah. This one would be the most common one. But let's say, let me get rid of these other three. Let's say they gave you this, and they want you to work backwards and figure out that. Well, if you have it on a grid, you could just count. 1, 2, 1, 2, 3. Easy enough. But let's just say they didn't give you a grid. All they did was give you this. Coordinate at that point is 6, 3. And that's a coordinate, so I'm using parentheses. And the coordinate of this point is 8, 6. Does anybody see what you can do with these two coordinates to somehow get the vector 2, 3? Yeah.
You can subtract them.
Yeah, you can subtract them. And you do have to subtract them in a certain order. This is the terminal. This is the initial. You want to subtract them. Terminal minus initial. 8 minus 6 gives you 2. 6 minus 3 gives you 3. And that's the last formula we'll write down. if what we're calculating using that formula is called a position vector. So to find a position vector, you're going to subtract your coordinates. What a position vector is a vector that starts at the origin. That's called a position vector. And if you're given a vector that doesn't start at the origin, okay, like the one I have over here, you can figure out what it would be if it did start at the origin by using the following formula that someone just told us. First of all, they'll give you where the vector starts, and they'll tell you where the vector stops. If they don't tell you which point is which, P1 is always the start point. P2 is always the terminal point. Yes?
Can you just scroll up a little bit? A little more. A little more. A little more. A little. Nope. A little down. Perfect. Good. Thank you.
Yep, you're welcome. So vector with initial point at the origin, that's called a position vector. How do you find a position vector? Yep. So you take where the vector starts, take where the vector stops, and subtract those two coordinates. Terminal minus initial for the x's, and terminal minus initial for the y's. And that will give you a position vector. All right, so we'll finish up by finding one of those, and that'll be it. It is important when you write a vector that you use those brackets around it. If you just put two numbers, well, that's called a list, just numbers separated with a comma. If you put parentheses, okay, well now that's called a coordinate. And if you put the angle brackets around it, that's a vector. One way of writing a vector. All right, so here's our point. Find the position vector. P1 is the start point, P2 is the stop. What's going to be my calculation to find the horizontal component of my position vector? Eli?
4 minus -1.
Yep, 4 minus -1. And what's going to be the calculation to find the vertical component of my position vector? Okay.
6 minus 2.
6 minus 2. So what would be the final answer for my vector? Yeah.
5,4.
5, 4. So if you wanted to draw this vector from the origin, you would go 5 right, 4 up, and draw it that way. This one did not start at the origin. All right, questions on that? All right. So the homework, remember this page 344 is a different book, but if you go to the PDF, it'll be the right page you need. It's all evens, except on 26 to 32, they ask you to do 2 different things in the direction. You don't have to do the second thing, it won't make sense yet. So all I want you to do in 26 to 32 is find the position vector, and that's it.